Hidden in the oldest light in the universe, scientists discovered something impossible: circular patterns, repeating structures that should not exist if the Big Bang was truly the beginning. Nobel Prize winner Roger Penrose claims these are scars from a previous universe, one that died before ours was born. We are about to explore black hole radiation that spans beyond time, cosmic signals that break every rule, and evidence that reality might be an endless cycle. If you enjoy this journey through the impossible, hit that like button and subscribe. Let's dive into the evidence. In 2010, a team analyzing data from the Wilkinson Microwave Anisotropy Probe noticed something strange: circles, perfect rings embedded in the cosmic microwave background radiation, the oldest light we can detect. These patterns appeared in multiple locations across the sky, and they should not exist. The cosmic microwave background is the afterglow of the Big Bang, light that has traveled for over 13 billion years to reach us. According to standard cosmology, this radiation should show random fluctuations, hot and cold spots scattered across space with no repeating patterns. Think of it like static on an old television, noise without design. However, these circles were different. They showed up as concentric rings of uniform temperature, some spanning areas larger than the full moon in our sky. The odds of such patterns forming randomly are astronomically low, something like 1 chance in several trillion. Roger Penrose, the mathematician who would later win the Nobel Prize for his work on black holes, immediately recognized what others dismissed. He published a paper suggesting these circles might be Hawking points, remnants of supermassive black holes that evaporated in a universe that existed before ours. The scientific community responded with heavy skepticism. Most cosmologists believe the Big Bang marked the absolute beginning of time and space. Nothing could come before because there was no before. Penrose was proposing something radical, that our universe emerged from the ashes of a previous cosmos, and these circles were the proof burned into the sky. The patterns were not isolated incidents. Research teams identified dozens of these structures, each one showing the same characteristics: temperature variations that formed perfect spheres when mapped in 3 dimensions. The mathematical probability of this happening by chance kept shrinking with each new discovery. What made these circles even more compelling was their uniformity. If they were random quantum fluctuations from the early universe, they should show irregularities, asymmetries, chaos. Instead, they displayed an eerie consistency, as if something specific created them, something that happened before time began. Yet the data remained controversial. Some scientists argued the circles were statistical artifacts, patterns the human brain wants to see in randomness. Others pointed out flaws in the analysis methods. The debate grew heated because the implications were staggering. If these circles were real, everything we thought we knew about the beginning of reality was wrong. However, the circles were just the first clue. What came next would make them look simple. Roger Penrose did not stumble into this theory by accident. For decades, he studied the mathematics of black holes, working alongside Stephen Hawking to prove that singularities, points of infinite density, must exist inside them. His equations revealed something disturbing about the far future of our universe. In trillions upon trillions of years, every star will burn out. Galaxies will drift apart as space expands. Black holes will evaporate through Hawking radiation, a process where quantum effects cause them to slowly lose mass. Eventually, the universe will reach a state of maximum entropy, a condition where no energy remains to do work, no structure can form, and time becomes meaningless. Penrose asked a question nobody else considered seriously. What if that end state is actually identical to a new beginning? His theory, called Conformal Cyclic Cosmology, proposes that when the universe reaches maximum entropy, the concept of scale disappears. In a universe with no massive particles left, only photons and other massless radiation, size becomes relative. An infinite cold universe and an infinitely small hot point become mathematically equivalent. This is where the geometry gets wild. Penrose used conformal transformations, a type of mathematical stretching that preserves angles while changing distances. Under these transformations, the infinite future of one universe can be mapped onto the Big Bang of the next. The end becomes the beginning. Think of it like a video game where walking off one edge of the screen makes you appear on the opposite side. Except instead of screen edges, it is the entire timeline of existence wrapping back on itself. When our universe grows, so old that time loses meaning, boom, it reboots as a new Big Bang. The theory explains those mysterious circles in the cosmic microwave background. Before our Big Bang, supermassive black holes existed in the previous universe. As they evaporated through Hawking radiation, they released enormous bursts of energy. These energy releases left imprints that survived the transition between universes, showing up in our sky as those perfect rings. Critics hammered the theory from every angle. They claimed Penrose was stretching mathematics beyond what physics allows. They argued that information cannot survive a Big Bang. They said the evidence was too weak, too speculative, too convenient. Penrose doubled down. He gathered more data, refined his calculations, and published detailed predictions about what future observations should find if his theory was correct. He specified the exact characteristics these Hawking points should display, including their size distribution and temperature signatures. The theory was now testable. Other physicists began taking it seriously. Some because the mathematics was elegant and consistent. Others because the alternative, that the Big Bang was a one-time event emerging from absolute nothingness, seemed equally impossible. At least Penrose offered a mechanism, a process, a reason why universes exist. The real bombshell was still coming though. Hawking radiation, named after Stephen Hawking, who predicted it in 1974, is one of the strangest confirmed phenomena in physics. Black holes are not completely black. They emit radiation because of quantum effects at their event horizons, the boundary beyond which nothing escapes. Here is how it works. In empty space, particle and antiparticle pairs constantly pop into existence and annihilate each other. This happens everywhere, all the time, at scales too small to notice. However, near a black hole's event horizon, something different occurs. One particle falls into the black hole while its partner escapes. To an outside observer, the black hole appears to emit radiation. This process is incredibly slow for stellar mass black holes. A black hole with the mass of our star would take 10 to the power of 67 years to evaporate completely. A number so large it makes the current age of the universe look like a blink. However, supermassive black holes, the monsters at the centers of galaxies with billions of times more mass, would take even longer. Penrose calculated what happens when these giants finally evaporate in the previous universe. The last moments of a supermassive black hole would release a tremendous spike of energy, like a dying star going supernova, except concentrated into a tiny point. This energy burst would be one of the last events in that dying cosmos. When the universe transitions from its infinite future to a new Big Bang through conformal geometry, these energy spikes leave marks. They create regions of slightly higher or lower temperature in the newborn universe's radiation field. Over billions of years, as that radiation cools and stretches across expanding space, the marks become those circular patterns we detect today. The beauty of this idea is its specificity. Penrose did not just say vague patterns should exist. He predicted their exact properties. Hawking points should appear as concentric circles because the spherical radiation from a black hole's evaporation maps to spheres in the new universe. They should have particular temperature profiles, warmer centers fading to cooler edges. When Daniel Ahn, Christoph Meissner, and Paweł Nurowski analyzed the Planck satellite data in 2018, they found exactly what Penrose predicted. They identified over 5,000 potential Hawking points, each showing the expected characteristics. The statistical significance was strong enough to publish in a major physics journal. Skeptics immediately attacked the methodology. They ran their own analyses and claimed the patterns were not statistically significant. They argued that if you search enough random data for any specific pattern, you will eventually find it. The debate became technical, focusing on statistical methods and data processing techniques. However, here is what made the Hawking point evidence compelling even to skeptics. The circles were not randomly distributed. They clustered in ways that matched predictions about how supermassive black holes were distributed in the previous universe. If they were statistical noise, this correlation should not exist. Furthermore, the temperature variations matched theoretical predictions with surprising accuracy. The amount of energy Penrose calculated should be released by evaporating black holes, aligned with the temperature differences measured in the circles. This was not just finding patterns, it was finding the right patterns with the right properties. The implications were staggering. If these really were Hawking points, we were detecting signals from a universe that died before time began. We were seeing through the Big Bang into a previous reality. Every assumption about the beginning of existence was crumbling. What happened next split the physics community even further. Conformal cyclic cosmology sounds complicated. However, the core idea is surprisingly simple. Universes die and are reborn in an endless cycle, each one emerging from the death of the one before. Our universe is just one link in an infinite chain. The cycle works like this. A universe begins with a Big Bang, hot and dense, expanding rapidly. Stars form, galaxies cluster, life emerges on countless worlds. Trillions of years pass, stars burn out, black holes grow, galaxies drift apart. Eventually only radiation remains, photons wandering through an ever-expanding void. At this stage, something profound happens. With no massive particles left, no atoms or planets or black holes, the universe loses its sense of scale. Photon traveling through infinite space has no reference point to measure distance or time. Mathematically, this infinite cold state becomes identical to an infinitely small hot point. Penrose uses conformal geometry to describe this transition. Imagine taking a photograph and stretching it infinitely in all directions. The image changes size, however, the shapes and angles remain the same. Conformal transformations work similarly in space-time, preserving certain properties while changing others. When applied to cosmology, these transformations show that the infinite future of a dead universe can be smoothly connected to the Big Bang of a new one. The end of time becomes the beginning of time. Space stretched to infinity collapses to a point. The cycle repeats. Each universe in the chain, called an aeon, lasts roughly 100 trillion years, though this number varies. Our aeon began 13.8 billion years ago, with our Big Bang. Before that, another aeon existed, possibly for quadrillions of years. Before that, another and another, backwards into infinity. The theory solves several deep problems in cosmology. One is the low entropy problem. Our universe began in an incredibly ordered state, all matter and energy concentrated in a tiny region. Why did it start so organized instead of chaotic? Conformal cyclic cosmology answers that the previous universe's high entropy end state naturally transitions to a new universe's low entropy beginning. Another problem involves the arrow of time. Why does time flow forward? Why do we remember the past instead of the future? In Penrose's model, the arrow of time is reset with each new aeon. The symmetry breaking that creates a temporal direction happens fresh with every Big Bang. The theory even addresses dark energy, the mysterious force accelerating the universe's expansion. In conformal cyclic cosmology, dark energy plays a crucial role in stretching space-time to the point where the conformal transition can occur. Without it, the cycle could not continue. Critics point out numerous challenges. How does information transfer between aeons? If everything is radiation at the end, how do the Hawking points preserve structure? What triggers the actual transition from end to beginning? Penrose has mathematical answers, however, they require accepting frameworks that many physicists find uncomfortable. The recycling model also creates philosophical puzzles. If the cycle is infinite, was there ever a first universe? Or has this process been happening forever, with no ultimate origin? And if information from previous aeons survives, could advanced civilizations leave messages across the boundary? Some researchers have taken this last question seriously. They have proposed searching for artificial patterns in the cosmic microwave background, signals deliberately placed by intelligent beings in the previous universe to communicate with us. So far, nothing has been found. However, the search continues. The real test of conformal cyclic cosmology comes down to predictions. If it is correct, future observations should reveal more Hawking points with increasingly precise characteristics. The theory also predicts specific features about gravitational waves from the early universe. These predictions make it scientific, falsifiable through experiment. What remains unclear is whether we will ever gather enough evidence to prove it definitively. The death of our universe will not be violent. No explosion, no collapse, no dramatic end. Instead, it fades away over timescales that dwarf the current age of existence by factors too large to comprehend. Understanding this slow decay is essential to grasping how the cycle could work. Right now, our universe is roughly 13.8 billion years old. Stars are still forming, galaxies are still colliding, energy is still abundant. However, this is just the opening chapter of a story that will last incomprehensibly longer. In about 1 trillion years, the last stars will form. Hydrogen clouds, the fuel for star formation, will be used up or scattered too thinly to collapse under gravity. After that, the universe enters what astronomers call the degenerate era, when stellar remnants like white dwarfs and neutron stars dominate. These remnants slowly cool. White dwarfs, the corpses of stars like our own, fade from white to red to black over trillions of years. Neutron stars, incredibly dense spheres of crushed matter, undergo a similar cooling process. The universe grows darker and colder with each passing millennium. Around 10 to the power of 40 years from now, protons themselves begin to decay. This is theoretical, based on certain physics models. However, if correct, it means even the atoms that make up matter will slowly disintegrate into radiation. Planets, asteroids, the remnants of dead stars, all will dissolve into particles of light. Black holes become the last remaining structures. However, even they are not immortal. Through Hawking radiation, they evaporate. Smaller black holes go first, vanishing in cosmic eye blinks of mere trillions of years. Supermassive black holes, the behemoths at galaxy centers, persist much longer. A black hole with 1 million times the mass of our star would take 10 to the power of 83 years to evaporate. The truly colossal ones, with billions of solar masses, could last 10 to the power of 100 years or more. These numbers are so vast that trying to grasp them breaks intuition. During this time, space continues expanding. Galaxies that were once neighbors drift beyond each other's cosmic horizons, moving so far apart that light from one can never reach the other. The universe becomes a collection of isolated regions, each containing perhaps a single evaporating black hole, or just empty space. Eventually, even the black holes finish evaporating. What remains is pure radiation, photons wandering, through a void that grows larger every second. The temperature approaches absolute zero. No stars shine, no structures exist, no change occurs. This is heat death, maximum entropy, the state where the universe has exhausted all useful energy. In classical thermodynamics, this is the final chapter. The universe reaches thermal equilibrium, and nothing interesting can ever happen again. Time becomes meaningless, because no processes remain to mark its passage. However, Penrose saw something others missed. In this state of pure radiation, with no massive particles to define scale, the universe loses its size. A photon has no rest mass, and experiences no passage of time in its own reference frame. To that photon, traveling forever through infinite space is indistinguishable from existing in a point. This is the key to the transition. When scale becomes undefined, conformal geometry allows the infinite future to curve back into a new beginning. The heat death is not an ending, but a transformation. The universe does not die, it is reborn. The energy that powers the new Big Bang comes from the geometry itself, from the way space-time reshapes during the transition. This is not creation from nothing. It is recycling from everything. Every photon, every scrap of radiation from the old universe gets compressed and energized into the conditions for a new expansion. Penrose's mathematics show this transition is smooth, inevitable, and preserves certain patterns like those Hawking points. The universe, in this view, is not a temporary event, but an eternal process. Birth, expansion, cooling, death, rebirth, over and over. Yet the question that haunts this model is also its greatest mystery. Asking what happened before the Big Bang seems like asking what is north of the North Pole. If time itself began with the Big Bang, there is no before. The question is meaningless. This has been the standard answer for decades. Penrose's theory demolishes that answer. In Conformal Cyclic Cosmology, time does not begin with the Big Bang. It continues from the previous aeon, flowing through the transition like a river bending around a corner. Our Big Bang was not the start of time, it was a reset, a phase change, a moment when the rules shifted. Understanding this requires rethinking what time actually is. We experience time as a sequence of moments flowing from past to future. Clocks tick, entropy increases, causes precede effects. However, at the deepest level, time might be an emergent property of the universe's structure rather than a fundamental dimension. In the far future, when the universe is nothing but radiation, clocks stop meaning anything. There are no atoms to vibrate, no processes to measure. Time still technically exists in the mathematical sense, however, nothing happens to mark its passage. The universe enters a state physicists call timelessness, where change ceases. This timeless state, however, is also a timeless beginning, because the TUI conformal transformation maps the infinite future to a dense point. What seems like eternal stasis in one frame looks like explosive expansion in another. Time loops back on itself through geometry. The philosopher's question here cuts deep. If each aeon transitions to the next in an infinite cycle, was there ever a first aeon? Penrose's answer is no. The cycle has no beginning because it is infinite in both directions. Just as numbers extend infinitely in both positive and negative directions with no first number, aeons extend infinitely into the past and future. This creates a strange implication. Our Big Bang, which we call the beginning of the universe, is actually just one of infinite reboots. Before our aeon, another existed for trillions upon trillions of years. Before that, another. This chain extends backwards forever with no starting point. Some physicists reject this on principle. An infinite past, they argue, leads to logical contradoxes. If an infinite number of events already happened before now, how did we ever reach now? This is called the problem of traversing infinity, and it has troubled philosophers since ancient times. Penrose sidesteps this by arguing that infinity in mathematics does not work the same way as infinity in physical time. The conformal transformations compress infinite time into finite mathematical structures. What seems paradoxical from inside an aeon makes perfect sense in the larger geometric picture. Another challenge involves causation. If the Big Bang was not the beginning, what caused it? The answer in conformal cyclic cosmology is that the previous aeon's end caused our beginning. However, what caused that previous aeon? Another one before it. The chain of causation has no ultimate source because it is infinite. This bothers many people. We are used to explanations that trace back to some fundamental cause, some first mover, some reason why anything exists at all. Penrose's model offers no such comfort. Existence just is, eternal and self-perpetuating. The religious and philosophical implications have sparked intense debate. Some see the theory as undermining the need for a creator. Others argue it raises even deeper questions about why this particular eternal cycle exists, instead of nothing. The scientific content remains separate from these interpretations. However, the boundary between physics and philosophy blurs at these scales. From a practical standpoint, verifying time's infinite past is impossible. We cannot observe previous aeons directly. The only evidence we have are those potential Hawking points, faint marks left by the final moments of the universe before ours. Even if they are real, they only prove one previous aeon existed, not an infinite chain. However, the mathematical consistency of the model counts for something. If the equations work, if they make testable predictions, if they solve problems that other theories cannot, then the infinite past becomes a feature rather than a bug. Time without beginning might be the truth we have to accept. The next piece of evidence, though, comes from somewhere unexpected. The cosmic microwave background radiation is the most precisely measured thing in all of cosmology. Satellites like COBE, WMAP, and Planck have mapped it to extraordinary detail, revealing temperature fluctuations smaller than 1 part in 100,000. These measurements have confirmed the Big Bang theory with stunning accuracy. Yet hidden in that precision are anomalies nobody can fully explain. The first strange feature is the cold spot. Discovered in 2004, it is a region of the sky where the cosmic microwave background is significantly colder than surrounding areas. This void spans nearly 1 billion light-years across, large enough to contain 10,000 galaxies. Standard cosmology struggles to explain its existence. Random quantum fluctuations in the early universe should create temperature variations. However, the cold spot is too large and too cold to match statistical predictions. The odds of it forming by chance are less than 1 in several thousand. Some scientists proposed it might be a supervoid, a region where galaxies are scarcer, causing photons to lose energy as they travel through. However, surveys of galaxy distributions do not show a void large enough to create the effect. The mystery deepened with each study. Penrose's theory offers a different explanation. If the cold spot is a Hawking point, a scar from an evaporating black hole in the previous aeon, its size and temperature make sense. The largest black holes would leave the biggest marks. The cold spot might be the signature of a truly monstrous black hole, one with hundreds of billions of solar masses. Another anomaly is the axis of evil, a term astronomers use only half-jokingly. It refers to an unexpected alignment of the largest temperature fluctuations in the cosmic microwave background. These fluctuations should be randomly oriented, however, instead, they line up along a specific axis through space. This alignment has been confirmed by multiple satellites. It is real, repeatable, and completely unexpected. The standard Big Bang model offers no explanation for why the universe would have a preferred direction. Space is supposed to be isotropic, the same in all directions. Again, conformal cyclic cosmology provides a potential answer. If the previous aeon had large-scale structure, perhaps a cluster of supermassive black holes aligned in a particular way, their Hawking points could create an axis in our aeon. The alignment would be an inheritance from the universe before. Then, there are the anomalous correlations. Temperature fluctuations at different scales should be independent. However, the Planck data shows unexpected relationships between them. Large-scale patterns influence small-scale patterns in ways that do not match the standard model's predictions. These correlations are subtle, appearing only in detailed statistical analysis. Mainstream cosmologists often attribute them to instrumental effects or processing artifacts. However, some researchers believe they represent real features requiring new physics to explain. Penrose and his collaborators argue these anomalies form a consistent pattern pointing toward conformal cyclic cosmology. Each strange feature, considered alone, might be dismissed as coincidence or error. Taken together, they suggest something profound about our universe's origin. Critics counter that searching for anomalies in highly complex data will always find something. The cosmic microwave background contains billions of data points. With that much information, patterns will emerge by pure statistics. Distinguishing real signals from noise is notoriously difficult. The debate centers on methodology. Penrose's team uses specific statistical tests designed to identify Hawking points. Skeptics run different tests and get different results. Both sides publish papers. Both sides claim the data supports their interpretation. What makes this particularly frustrating is that the cosmic microwave background is a one-time measurement. We have one sky, one set of temperature fluctuations. We cannot rerun the Big Bang to get more samples. Statistical arguments remain forever uncertain. However, new observations might break the stalemate. Future missions planned to study cosmic microwave background polarization could reveal additional patterns. Gravitational wave detectors might pick up signals from the early universe that either confirm or refute conformal cyclic cosmology. For now, the anomalies remain unexplained by standard cosmology. They might be nothing, random quirks of chance in how our universe happened to form, or they might be exactly what Penrose claims, echoes of a dead universe whispering through the Big Bang. The answer to that question depends on what happens to information when black holes die. In 1974, Stephen Hawking shocked the physics world by proving black holes are not completely black. They radiate, they shrink, and eventually they disappear entirely. However, his discovery created one of the deepest paradoxes in theoretical physics, a problem that remains unsolved 50 years later. The paradox is simple to state. Black holes destroy information. Anything that falls past the event horizon, whether a star, a planet, or a single particle, loses its unique properties. The black hole grows slightly in mass, however, all the specific details about what fell in seem to be erased forever. However, quantum mechanics has an ironclad rule. Information cannot be destroyed. The state of any quantum system at one moment determines its state at future moments. If you know everything about a system now, you can calculate everything about it later. This reversibility is fundamental to how quantum physics works. Hawking radiation appears to violate this rule. The radiation coming from a black hole is thermal, meaning it is random, featureless, and carries no information about what created it. If black holes evaporate completely through Hawking radiation, everything that fell in would be lost forever. Information would be destroyed, breaking quantum mechanics. This contradiction, called the black hole information paradox, has tormented physicists for decades. Either quantum mechanics is wrong, general relativity is wrong, or we misunderstand something profound about how black holes work. Stephen Hawking himself believed information was destroyed, arguing that quantum mechanics must be modified. Other physicists, led by Leonard Susskind, insisted information must escape somehow, perhaps encoded in subtle correlations in the Hawking radiation. The debate grew heated. In 2004, Hawking conceded he was wrong and accepted that information must be preserved. However, he never explained how. The mechanism by which information escapes from an evaporating black hole remains mysterious. Current research explores ideas like holography, quantum entanglement, and modifications to the event horizon structure. Penrose's Conformal Cyclic Cosmology enters this debate from an unexpected angle. If black holes from the previous aeon evaporate into Hawking radiation that transitions into our Big Bang, what happens to the information they contained? According to Penrose, some information does carry through the transition. The Hawking points themselves are information, patterns showing where and when supermassive black holes evaporated. Their positions, sizes, and energy signatures encode data about the previous universe's structure. However, the vast majority of information is lost. Penrose argues this is acceptable because the conformal transition resets the universe's state. Only certain large-scale patterns survive, enough to leave those circular marks, but not detailed quantum information about individual particles. This position puts him at odds with many quantum physicists who insist information conservation is absolute. If conformal cyclic cosmology allows information destruction, even partially, it might be fundamentally incompatible with quantum mechanics. Some researchers have tried to reconcile this. They propose that information is not destroyed, but transformed in ways we do not yet understand. The conformal transition might scramble quantum states into new configurations that preserve information mathematically while appearing to destroy it physically. Another possibility is that information is encoded in the geometry of spacetime itself. Just as a hologram stores three-dimensional information on a two-dimensional surface, the universe might store all its information in its structure. The transition between aeons could preserve this geometric information even as particles and radiation transform. The implications extend beyond cosmology. If information can be destroyed in principle, even in the extreme conditions of a dying universe transitioning to a new Big Bang, it changes how we think about reality. The history of the universe might not be recoverable from its current state. The past could be genuinely lost. For conformal cyclic cosmology, this creates both challenges and opportunities. If the theory can solve the information paradox, showing how information flows through black holes and across aeons, it would be a tremendous success. If it cannot, the theory might fail on fundamental grounds. Recent work on black hole thermodynamics and quantum gravity might provide answers. Researchers studying how information behaves near event horizons are discovering that the distinction between inside and outside a black hole is more subtle than previously thought. Information might leak out gradually as the black hole evaporates, encoded in complex quantum correlations. If this is true, then the final burst of radiation as a supermassive black hole evaporates could carry enormous amounts of information. This radiation, transformed through the conformal transition, might encode far more about the previous universe than just position and energy. Detailed structure could survive. Testing these ideas requires understanding quantum gravity, the still undeveloped theory that unifies quantum mechanics and general relativity. Until we have that theory, the information paradox and its implications for conformal cyclic cosmology remain open questions. What we know for certain is that something strange happens when black holes die. If conformal cyclic cosmology is correct, and universes die and are reborn in an endless cycle, a disturbing question emerges. Could the exact same universe repeat? Could our Big Bang happen again, creating identical galaxies, identical planets, identical you living identical lives? This is not just philosophy. It is a mathematical consequence of infinite time. If the cycle continues forever, and if there are only a finite number of ways to arrange matter and energy in a universe, then repetition becomes inevitable. Infinity guarantees that every possible configuration will occur infinitely many times. The idea has ancient roots. Nietzsche proposed eternal recurrence, the notion that all events will repeat exactly across infinite time. However, he was making a philosophical point about how to live. Conformal cyclic cosmology makes it a physical prediction. Consider the numbers involved. Our observable universe contains roughly 10 to the power of 80 particles. That is a huge number, however, it is finite. The number of ways to arrange those particles, while astronomically large, is also finite. Given infinite time and infinite aeons, every arrangement will occur. This means somewhere in the infinite sequence of past aeons, a universe existed exactly like ours. Every atom in the same position, every star burning the same way, every person living the same life, thinking the same thoughts, making the same choices, an exact copy. Furthermore, an infinite number of such copies must exist in the past and future. You have lived this exact life infinite times before and will live it infinite times again. The thought is either comforting or horrifying depending on how satisfied you are with your existence. Penrose acknowledges this possibility, however, does not dwell on it. His focus is on the physics of the transition, the evidence for previous aeons, the testable predictions about what we should observe. Whether exact repetition occurs is almost beside the point. However, other physicists take it seriously. If exact repetition is inevitable, it creates paradoxes about identity and causation. Are you the same person as your copy in a previous aeon? Do your actions matter if they will be repeated exactly, infinitely? Some researchers argue that even in infinite time, exact repetition might never occur. Quantum mechanics introduces true randomness, and perhaps the possible configurations of the universe are actually infinite rather than finite. Each aeon might differ from all others in subtle ways. Another escape comes from the nature of the conformal transition itself. If the transformation between aeons does not preserve all information, then each cycle starts with slightly different initial conditions. The universe could loop infinitely without ever repeating exactly. Yet, even without exact repetition, statistical repetition seems unavoidable. Given enough aeons, you will have countless near copies, people almost identical to you living almost identical lives in almost identical universes. The distinction between exact and approximate repetition becomes philosophical rather than physical. The infinite loop raises questions about progress and meaning. If civilizations rise and fall across aeons, if knowledge is gained and then lost in the reset, what is the point? Does anything we accomplish matter if it will all dissolve into radiation and be forgotten? Penrose's theory offers no comfort on this front. The cycle is mechanical, driven by geometry and thermodynamics, indifferent to our hopes or achievements. We are temporary patterns in a universe that will outlast us by incomprehensible margins. Some philosophers find this liberating. If nothing lasts, then we are free to create meaning for ourselves without needing cosmic justification. Others find it nihilistic, stripping existence of ultimate purpose. From a scientific perspective, the infinite loop problem is less troubling. Science does not deal in ultimate meanings. It describes how things work, not why they matter. Conformal cyclic cosmology could be correct regardless of its philosophical implications. The real challenge is testing it. If we live in one of infinite aeons, how can we determine our place in the sequence? Are we early or late in the chain? Have countless civilizations existed before us? Or are we among the first intelligent beings in this eternal cycle? The Hawking points might provide clues. By studying their distribution and properties, we might infer characteristics of the previous universe. Were there many galaxies? How clustered were the black holes? Did structure form differently than in our aeon? Such detective work could, in principle, let us peer back through one transition. However, going further seems impossible. Each Big Bang erases most information from the previous aeon, leaving only faint traces. The chain of evidence breaks after one link. Unless, of course, something survives better than we think. When Roger Penrose first published his ideas about conformal cyclic cosmology in 2005, the response from the physics community ranged from skeptical to hostile. Major cosmologists dismissed it as mathematical speculation, untethered from reality. Journals rejected papers on the topic. Grant funding dried up for anyone pursuing the theory seriously. This resistance was not simply stubbornness or closed-mindedness. The scientific establishment had good reasons to push back. Reasons rooted in how physics advances and how extraordinary claims require extraordinary evidence. First, the standard Big Bang model works spectacularly well. It predicts the cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies, and countless other observations. Decades of data confirm it. Replacing a successful theory demands overwhelming evidence that the new theory explains everything the old one did, plus solves problems the old one could not. Penrose's theory, for all its mathematical elegance, struggled on this front. It explained the mysterious circles in the cosmic microwave background. However, standard cosmology could potentially explain those as statistical flukes. It addressed the arrow of time and the low entropy problem. However, alternative solutions existed. The evidence was suggestive, compelling to some, but not definitive. Second, the theory made uncomfortable demands on conventional physics. It required accepting that the infinite future and the Big Bang are the same thing through conformal transformations. Many physicists found this geometrical sleight of hand too abstract, too removed from observable reality. The mathematics might work. However, did it describe the actual universe? Third, conformal cyclic cosmology appeared to conflict with quantum mechanics in subtle ways. The information paradox, the nature of the transition, the survival of patterns across aeons, all these raised questions that Penrose could not fully answer. Without a complete quantum theory of gravity, the model seemed incomplete at best, flawed at worst. The cultural dynamics of science also played a role. Cosmology had coalesced around certain frameworks: inflation, dark matter, dark energy, string theory. Researchers built careers on these ideas. Entire collaborations formed to test their predictions. Penrose's theory threatened to upend that consensus, and humans, even scientists, resist having their life's work questioned. Personal factors mattered too. Penrose was a mathematician, not primarily a cosmologist. His work on black holes was legendary, his Nobel Prize well-deserved. However, this did not give him automatic credibility in early universe physics. Some cosmologists felt he was stepping outside his domain. The media attention made things worse. Penrose's theory received coverage in popular science outlets, which framed it as overthrowing established cosmology. This irritated researchers who felt the public was being misled about the strength of the evidence. Science by press release, as one critic put it, does not advance knowledge. However, the resistance began to crack. In 2010, the discovery of those circular patterns in WMAP data forced a reckoning. Even skeptics had to admit something strange was there. Was it really evidence for a previous universe, or were the critics right that it was statistical noise? Research teams on both sides published detailed analyses. Some confirmed the patterns and their statistical significance. Others argued the methods were flawed and showed how similar patterns could arise randomly. The debate grew technical, focusing on autocorrelation functions, multipole expansions, and Bayesian statistics. A key turning point came when the Planck satellite, with its superior resolution and sensitivity, released data. Penrose's team immediately analyzed it and found even more Hawking points than before. The circles were not artifacts of WMAP's lower resolution. They appeared in the better data too. Still, mainstream cosmology held firm. Several high-profile physicists published rebuttals, arguing the Planck data showed no such patterns when analyzed correctly. The disagreement hinged on which statistical tests were appropriate and how to interpret borderline results. Funding agencies began to notice. If there was even a chance Penrose was right, it warranted investigation. Grants were awarded for follow-up studies. Younger researchers, less invested in the standard model, started exploring conformal cyclic cosmology seriously. The theory's predictive power helped. Penrose specified what future observations should find if he was correct. This falsifiability made the theory scientific rather than speculative. Whether it was right or wrong, it could be tested, and that is all science requires. By 2020, the hostility had softened into productive disagreement. Conferences featured debates between supporters and critics. Both sides acknowledged the data was complex and the interpretations uncertain. The question shifted from whether conformal cyclic cosmology was crazy to whether it might be true. However, the real test would come from new telescopes and new data, evidence that could settle the debate once and for all. Conformal geometry sounds abstract. However, it is the key that unlocks Penrose's entire theory. Understanding even a simplified version reveals why the infinite future of a dying universe can become the Big Bang of a new one. The mathematics is strange, elegant, and shockingly consistent. Start with a simple idea. Geometry deals with shapes, distances, and angles. In normal Euclidean geometry, if you stretch or shrink a shape, you change it. A circle becomes an ellipse if stretched unevenly. However, conformal transformations are different. They preserve angles while allowing distances to change. Imagine drawing a triangle on a rubber sheet. Now stretch the sheet in all directions equally. The triangle gets bigger, however, the angles at its corners stay the same. That is a conformal transformation. The shape's size changes, however, its angular relationships remain intact. In space-time, conformal transformations do something remarkable. They can stretch coordinates infinitely, making a finite region appear infinite, or compress an infinite region into a finite one. Crucially, they preserve the causal structure of space-time, the relationships between events that can influence each other. Penrose applies this to cosmology through something called the conformal diagram. These diagrams represent the entire history of the universe on a finite page, even though space-time itself is infinite. Time runs vertically, space horizontally, and light rays travel at 45-degree angles. For our universe, the conformal diagram shows the Big Bang at the bottom, time flowing upward, and the infinite future at the top. Standard cosmology stops there. The diagram ends. However, Penrose noticed something. If the universe evolves to a state with only massless radiation, something special happens to the geometry. Massless particles, like photons, do not experience time. They have no rest frame where they sit still. From a photon's perspective, if photons could have perspectives, space and time are fundamentally different from how massive particles experience them. In a universe of pure radiation, scale becomes meaningless. When scale has no meaning, you can apply a conformal transformation that maps the infinite future onto a finite boundary. That boundary can then be connected to the Big Bang of a new aeon. The end becomes the beginning through pure geometry. The transformation is called a conformal rescaling. Mathematically, you multiply the metric, the mathematical object describing spacetime's geometry, by a factor that goes to 0 at infinity. This shrinks the infinite future down to a single point in the conformal diagram. That point, representing maximum entropy and infinite time, is geometrically identical to the Big Bang of the next aeon. The transformation is smooth, no discontinuities, no violations of physical laws, just geometry folding back on itself. Critics attack this from multiple angles. They argue that mathematical possibility does not equal physical reality. Just because you can perform a conformal transformation on paper does not mean the universe actually does it. The theory needs a mechanism, a physical process that drives the transition. Penrose responds that the mechanism is the geometry itself. When the universe reaches the state where conformal invariance holds, when only radiation exists, the transformation is not just allowed, but inevitable. The mathematics describes reality rather than imposing artificial structure on it. Another criticism involves energy conservation. Where does the energy for the new Big Bang come from? If the old universe has dissipated to near zero energy density, how does it reboot with the immense energy required for a hot, dense beginning? The answer lies in how energy is defined in general relativity. Energy is not a simple quantity in curved spacetime. It depends on the reference frame and the gravitational field. During the conformal transition, the energy of the radiation field gets rescaled. What appears as nearly zero in the dying universe becomes enormous in the new Big Bang frame. Think of it like changing currency. The same wealth looks different when measured in dollars versus cents. The conformal rescaling changes the units we use to measure energy, making a depleted universe into an energized one without violating conservation laws. The mathematics also explains why only certain patterns survive the transition. Large-scale structures like the Hawking points from evaporating black holes maintain their form under conformal transformations. Small-scale quantum fluctuations get scrambled and lost. This selectivity determines what information passes between aeons. Penrose and his collaborators have published hundreds of pages of equations working out the details. The theory is not vague hand-waving. It makes precise statements about metrics, curvature tensors, and field equations. The rigor is there for anyone willing to work through it. However, rigor does not guarantee truth. Physics is filled with mathematically beautiful theories that nature rejected. Supersymmetry, Certain string theory models and various unified field theories all had elegant mathematics. Observations did not confirm them. The real test comes from comparing predictions to data. Conformal cyclic cosmology predicts the distribution, size, and temperature profile of Hawking points. It predicts specific features in gravitational waves from the early universe. It predicts how certain cosmic anomalies should correlate. Some of these predictions have been checked against existing data with mixed results. The circles in the cosmic microwave background match expectations if you use certain statistical methods. They disappear if you use others. The ambiguity frustrates everyone involved. Future observations might resolve this. Next-generation gravitational wave detectors could pick up signals from cosmic strings or other relics that conformal cyclic cosmology predicts should exist. Better measurements of cosmic microwave background polarization could reveal additional patterns. Until then, the mathematics remains a beautiful edifice waiting for confirmation. It works on paper. Whether it describes a reality is the question that drives everything else. If Penrose is right, we are surrounded by signals from a dead universe. They permeate the cosmic microwave background, the oldest light we can observe, whispering through 13 billion years to tell us that something came before. The challenge is separating those whispers from noise. The search for these ghost signals requires unprecedented precision. The cosmic microwave background has been measured to extraordinary accuracy. However, finding subtle patterns within it pushes technology to its limits. Temperature differences of millionths of a degree matter. Statistical techniques must be refined beyond what most fields ever require. Researchers begin by mapping the entire sky at microwave frequencies. Satellites like Planck collected data across 9 frequency bands, building a picture of the cosmic microwave background at multiple wavelengths. This allows scientists to separate the primordial signal from foreground contamination, dust and gas in our own galaxy that emit microwave radiation. Once the foreground is subtracted, what remains is a map of temperature fluctuations from the early universe. Most of these fluctuations are random. Quantum variations stretch to cosmic size by the rapid expansion during the Big Bang's first fraction of a second. They followed a pattern called the power spectrum, which standard cosmology predicts quite accurately. However, buried within that randomness might be the Hawking points. These would appear as circular regions of correlated temperature variations. The key word is correlated. Random fluctuations should not show patterns that repeat in concentric rings. Finding such correlations is the smoking gun. The statistical method used is called matched filtering. You define what you expect a Hawking point to look like based on theory, then search the data for regions that match that template. This is similar to how facial recognition software works, scanning images for patterns that fit a face. Penrose's team developed specific templates based on how radiation from an evaporating black hole should appear after the conformal transition. They predicted the angular size, the temperature profile, and the variation from center to edge. Then they searched the Planck data. They found thousands of candidates. Each one was a region where the temperature fluctuations matched the expected pattern better than random chance would predict. The team calculated statistical significance using multiple methods and published their results. Immediately, other researchers tried to replicate the findings. Some succeeded, confirming the patterns existed. Others failed, finding no statistically significant signal. The discrepancy came down to technical choices in data processing, which statistical tests to use, how to account for looking in multiple places, and how to define statistical significance. This is where science gets messy. There is no universal agreement on the correct statistical approach for this problem. Different methods make different assumptions, and those assumptions matter enormously when dealing with borderline signals. What looks like a clear detection under one analysis vanishes under another. A major issue is the look elsewhere effect. If you search a large dataset for any specific pattern, you're likely to find it somewhere just by chance. Imagine searching a book for the phrase ghost signal. You will probably find ghost on one page and signal on another, purely by coincidence. How do you prove you found a real pattern rather than random matches? The solution is to predefine what you are looking for and where, then apply strict corrections for multiple testing. However, with the cosmic microwave background, this is complicated. The entire sky is the search space. Hawking points could be any size within a certain range and located anywhere. Accounting for all possible combinations is mathematically challenging. Skeptics argue that Penrose's team did not adequately correct for multiple testing. They claim the apparent detections are statistical artifacts, patterns the analysis method is biased to find even in random data. To test this, critics ran the same analysis on simulated skies with no Hawking points, just random fluctuations. They found similar patterns. Supporters counter that the simulations were not realistic. Real data has complexity that simple random fields lack. The patterns in real data show characteristics that simulations miss. The debate became a technical battle over simulation methods and statistical rigor. Another approach is to search for other types of ghost signals. Conformal Cyclic Cosmology predicts more than just Hawking points. It predicts specific patterns in gravitational waves, features in the large-scale structure of galaxies, and anomalies in the distribution of galaxy clusters. Gravitational wave detectors like LIGO and Virgo have begun probing the cosmos for ripples in space-time. Future space-based detectors will be sensitive to lower frequencies, potentially picking up gravitational waves from the early universe. If conformal cyclic cosmology is correct, these waves should show imprints from the conformal transition. Similarly, large galaxy surveys mapping the distribution of matter across billions of light years might reveal patterns inherited from the previous aeon. Correlations in how galaxies cluster could reflect structures that survived the Big Bang. No definitive ghost signals have been confirmed yet. Every claimed detection remains disputed. However, the search continues with improving technology and refined methods. Each new dataset offers another chance to find proof or deal a fatal blow to the theory. The frustrating reality is that ghost signals, if they exist, are subtle. They are not loud, obvious features, but faint impressions on the edge of detectability. Proving they are real requires not just finding them, but convincing skeptics who have every reason to demand extraordinary evidence. What makes this particularly challenging is that we get only one universe to study. The transition from a dying universe to a new Big Bang is the most mysterious part of conformal cyclic cosmology. Penrose describes the geometry, the mathematics, and the final state conditions. However, the actual moment of transformation, the mechanism that reboots existence, remains elusive. In standard cosmology, the Big Bang simply is. It is the initial condition, the starting point from which everything evolves. Asking what caused it is considered outside the scope of physics because causation requires time, and time begins with the Big Bang. You cannot have a cause before time exists. Conformal cyclic cosmology rejects this limitation. The Big Bang has a cause, the death of the previous universe. However, how does that death trigger the birth? What is the physical process that turns maximum entropy into explosive expansion? Penrose's answer is rooted in the properties of space-time itself. When the universe reaches a state of pure radiation, all massive particles having decayed or been absorbed by long evaporated black holes, something fundamental changes. Mass is what gives meaning to scale, to size, to distance. A photon, traveling at the speed of light, experiences no passage of time. Its journey from emission to absorption, even if crossing billions of light years, takes zero time in its own frame. Similarly, distance becomes undefined. Without mass to provide reference points, the universe loses its ruler. In this massless state, the geometry of spacetime becomes what mathematicians call conformally invariant. The equations describing it remain unchanged under conformal transformations. This is not just a mathematical trick. It reflects a deep physical property of how radiation behaves. The conformal transformation that Penrose applies rescales the metric, the mathematical description of distances and intervals. This rescaling maps the infinite future, where the universe has expanded forever and cooled to near absolute zero, onto a finite boundary. That boundary is then identified with the Big Bang of the next aeon. But identifying two things mathematically is different from explaining how one becomes the other. Critics push on this point. What physical process enacts the transformation? Is there a moment of transition, or does one universe smoothly blend into the next? Penrose suggests the transition is smooth in conformal time. Conformal time is a coordinate system where the entire infinite future maps to a finite value. In this coordinate system, reaching the end of one aeon and the beginning of the next is continuous, like walking from one country into another with no border crossing. However, in physical time, the time measured by clocks and experienced by observers, the transition is singular. The infinite future never arrives for any observer in the dying universe. They would see time slowing, processes halting, approaching but never reaching the asymptotic end. Meanwhile, the Big Bang of the new aeon explodes into existence. From its perspective, there was no before. Time starts, space expands, energy density is enormous. The transition, seen from inside either aeon, looks like a beginning or ending. Only from outside in the mathematical space of conformal geometry does the connection become clear. This dual perspective confuses many people. How can something be smooth in one coordinate system and singular in another? The answer is that coordinates are human choices, ways of labeling events. Physical reality does not care which coordinates you use. The geometry is what matters. The energy for the new Big Bang comes from the geometry itself. In general relativity, gravitational fields carry energy. During the conformal rescaling, the energy associated with the radiation, field, and the curvature of space-time gets amplified. What appears as dilute, low-energy radiation in the old universe becomes the intensely concentrated energy of the new Big Bang. Some physicists argue this violates energy conservation. Penrose counters that energy is not globally conserved in general relativity anyway. In an expanding universe, energy can be created or destroyed, because space-time itself is dynamic. The conformal transition is an extreme version of this, a moment where the definitions of energy and time undergo radical transformation. Another perspective comes from quantum cosmology. Some researchers have tried to describe the transition using quantum mechanics, treating the universe as a wave function that evolves according to quantum laws. In this view, the conformal transition might be a quantum tunneling event, where the universe tunnels from the end state of one aeon to the beginning state of the next. Quantum tunneling allows particles to pass through barriers they classically could not overcome. The universe might similarly tunnel through the apparent barrier between maximum entropy and a new Big Bang. The probability of this tunneling could be calculated from the wave function's properties, though nobody has successfully done this yet. There are also speculative ideas involving quantum gravity, the still undeveloped theory unifying quantum mechanics and general relativity. Perhaps at the Planck scale, the smallest meaningful length, quantum fluctuations in space-time geometry drive the transition. The smooth classical description Penrose offers might be an approximation of something fundamentally quantum. Testing these ideas is nearly impossible with current technology. We cannot recreate the conditions of a dying universe. We cannot observe the moment of the Big Bang directly. The transition, if it happens, occurs under conditions so extreme that known physics breaks down. What we can test are the consequences. If universes recycle, through this process, specific patterns should appear in the cosmic microwave background, gravitational waves, and large-scale structure. Finding those patterns would not explain the mechanism, however, it would confirm the transition happens. For now, how a new Big Bang is created remains the deepest mystery in conformal cyclic cosmology. The mathematics works. The observations hint at something. The mechanism remains hidden. One of the most mind-bending aspects of conformal cyclic cosmology is how something infinite becomes a point. The universe expands forever, growing larger without limit, yet somehow this infinite vastness transforms into the infinitely small, infinitely dense state of a new Big Bang. Understanding how this happens requires rethinking what size means. In everyday life, size is absolute. A meter is a meter, a mile is a mile. Objects have definite sizes that everyone agrees on. However, in physics, size is always relative. You measure one thing against another. Meter is defined by the distance light travels in a specific fraction of a second. A mile references physical objects or processes. Relativity takes this further. Different observers moving at different speeds measure different lengths and times. What appears contracted to one observer looks normal to another. Size depends on your reference frame, your state of motion, your location in a gravitational field. Conformal geometry pushes this to an extreme. It says that under certain conditions, absolute size becomes meaningless. Only angles, ratios, and relationships matter. You can stretch or shrink the entire universe, and if the physics is conformally invariant, nothing changes. This happens when the universe contains only massless particles. Mass provides a scale. The electron has a specific mass. That mass defines a natural length, the Compton wavelength, through quantum mechanics. With massive particles around, you have reference points for size. Photons have no mass. They define no intrinsic scale. A universe of pure radiation has no natural unit of length. You might think the wavelength of the photons provides a scale, however, wavelengths stretch as the universe expands. There is no fixed reference. In such a universe, calling it large or small is arbitrary. You can rescale all distances by any factor, and the physics remains identical. This conformal invariance is the key to Penrose's theory. Imagine you are shrinking, getting smaller and smaller, while the universe around you stays the same size. Eventually you become microscopic, then atomic, then subatomic. Now imagine instead that you stay the same size while the universe grows, expanding to infinity. In a conformally invariant universe, these two scenarios are indistinguishable. Your shrinking to a point and the universe expanding to infinity are the same thing, just described differently. Scale becomes a choice of perspective rather than a physical fact. Penrose uses this to connect the infinite, future to a new beginning. As the dying universe expands forever, matter and energy dilute to nothing. Eventually only photons remain, wandering through an ever-growing void. The universe becomes conformally invariant. At this point, a mathematical transformation can map the infinite size onto a finite point. This is not physical compression, it is a coordinate change, a relabeling of events. The infinite future gets assigned a finite coordinate value called conformal infinity. That point of conformal infinity can then be identified with the Big Bang of the next aeon. They are the same event, viewed from different conformal frames. What looks like an infinite future in one aeon looks like a hot, dense beginning in the next. Critics find this deeply unsatisfying. It feels like mathematical sleight of hand, defining the problem away rather than solving it. How can something physically infinite become physically small? Words like mapping and identification sound abstract, disconnected from reality. Penrose argues that this objection misses how physics works. All our descriptions of nature are mathematical models. When we say space expands or time flows, we are using mathematical structures to represent reality. Those structures are our tools, not reality itself. If the mathematics shows that infinite expansion and a new Big Bang are equivalent under conformal transformations, and if the universe actually is conformally invariant at its end, then the transformation is not a trick. It is a description of what physically happens. Another objection involves quantum mechanics. Even if classical geometry allows the transformation, what about quantum fields? Do they behave the same under conformal rescaling? Massless quantum fields are indeed conformally invariant, supporting Penrose's case, however, massive fields are not. This raises the question of when exactly the universe becomes conformally invariant. All massive particles must decay or be absorbed. All black holes must evaporate. Even protons, if they decay as some theories suggest, must disappear. Only when absolutely nothing massive remains does the transformation become possible. The timescales involved are staggering. Proton decay, if it happens, takes at least 10 to the power of 34 years. Supermassive black holes evaporate over 10 to the power of 100 years. The universe must exist for incomprehensibly long before the conformal transition can occur. During this vast stretch of time, does anything happen? Is there change, evolution, any kind of process? Or does the universe enter a frozen state where nothing occurs because nothing can occur? Penrose's theory suggests that as the universe approaches conformal invariance, change slows. Processes that rely on energy gradients or mass halt. Eventually you reach a state where time, in any meaningful sense, stops. The universe exists, but does not evolve. This timeless state is what the conformal transformation maps to a new beginning. Time stopping at the end of one aeon is geometrically equivalent to time starting at the beginning of the next. The scale problem dissolves because scale itself disappears in a timeless, massless universe. Whether this explanation is satisfying depends on your philosophical comfort with mathematical abstraction. Some physicists embrace it as revealing deep truths about reality's structure. Others see it as evidence the theory is too disconnected from physical intuition to be correct. The debate continues because the scale problem touches on fundamental questions about what we mean by existence, size, and change. Conformal cyclic cosmology is not the only game in town. Multiple competing theories attempt to explain the same anomalies in the cosmic microwave background, the nature of the Big Bang, and the ultimate fate of the universe. Each offers different answers, different predictions, and different philosophical implications. Eternal inflation is perhaps the most popular alternative. Proposed by Alan Guth and refined by Andre Linde and others, it suggests that inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang, never completely stops. Instead, it continues forever in some regions of space while ending in others. Our universe is one bubble where inflation ended, allowing normal expansion, star formation, and galaxy development. However, beyond our cosmic horizon, inflation continues, spawning endless other bubble universes. This creates a multiverse, an infinite collection of separate universes, each with potentially different physical laws. Eternal inflation explains the low entropy beginning of our universe. It is just one pocket in a much larger inflating space. The question of what came before the Big Bang becomes less relevant because our Big Bang is one event among infinite others, all occurring within eternal inflation. This theory has strong observational support. The cosmic microwave, backgrounds at uniformity, the flatness of space, and the distribution of galaxies all match inflation's predictions. However, eternal inflation also faces problems. It is difficult to test because other universes are forever beyond our reach. It raises questions about probability and measure that remain unresolved. String theory offers yet another perspective. According to string theory, the fundamental constituents of reality are not particles, but tiny vibrating strings. Different vibration modes correspond to different particles. The theory requires extra dimensions beyond the 3 of space and 1 of time we experience. In some string theory models, our universe is a brane, a higher dimensional object, floating in a higher dimensional space called the bulk. The Big Bang might have resulted from our brane colliding with another brane. This ekpyrotic scenario, named after the ancient Greek idea of cosmic cycles through fire, shares some features with conformal cyclic cosmology. Brane, collisions could repeat, creating cycles of universes. However, the mechanism is completely different from Penrose's conformal transformation. The cycles involve higher dimensional dynamics rather than geometry rescaling. The evidence required to distinguish between them includes measurements of gravitational waves and cosmic strings that neither theory has yet explained conclusively. Loop quantum gravity, another approach to quantum gravity, suggests space itself is granular at the Planck scale. This discreteness could prevent the singularity of the Big Bang. Instead of infinite density, you get a big bounce, where a previous contracting universe rebounds into our expanding one. The Big Bounce models share conformal cyclic cosmology's cyclic nature, but through a different mechanism. Rather than an infinite expansion transitioning to a new beginning, a contracting universe reaches maximum density and bounces back. This avoids the singularity problem but raises questions about what causes the bounce and whether information survives through it. Each competing theory makes predictions. Eternal inflation predicts specific patterns in cosmic microwave background fluctuations and gravitational waves. String theory's brane collisions predict cosmic strings and particular gravitational wave signatures. Loop, quantum gravity's bounce, predicts specific modifications to the early universe's power spectrum. The challenge is that many predictions overlap. Different theories can explain the same observations through different mechanisms. Distinguishing them requires finding unique signatures that only one theory produces. Conformal cyclic cosmology's unique prediction is the Hawking points, those circular patterns from evaporating black holes in the previous aeon. No other theory predicts these specific features. If they are confirmed beyond doubt, conformal cyclic cosmology wins. If they are shown to be statistical artifacts, the theory suffers a potentially fatal blow. Proponents of other theories have their own stakes. Eternal inflation researchers are searching for signatures of bubble collisions, places where our universe bumped into another bubble. Finding such evidence would support the multiverse picture, while challenging conformal cyclic cosmology. String theorists want to find cosmic strings, defects in spacetime left over from the early universe. These would support string theory and ekpyrotic models, while being irrelevant to or even contradicting conformal cyclic cosmology. The competition is fierce but productive. Each theory pushes others to refine their predictions and confront their weaknesses. The scientific method thrives on this kind of rivalry, where multiple explanations compete for observational validation. What frustrates everyone is the difficulty of getting decisive evidence. The energies involved in the early universe are far beyond what particle accelerators can reach. The distances involved make direct observation impossible. We are left examining subtle patterns in ancient light and hoping they reveal secrets about reality's deepest nature. Some physicists worry that we have entered an era where theories are becoming untestable. If conformal cyclic cosmology, eternal inflation, string theory, and other frameworks all make predictions too subtle to verify with current or foreseeable technology, how do we choose between them? The pessimistic view is that cosmology will split into camps, each defending their preferred theory based on mathematical elegance, philosophical appeal, or personal intuition rather than experimental evidence. Science could degrade into something more like philosophy, interesting but not definitively resolvable. The optimistic view is that technology will advance. Better telescopes, more sensitive detectors, novel observational techniques might provide the crucial evidence. History shows that science often finds ways to test what seemed untestable. For now, all these theories remain in play, each with strengths and weaknesses, each with passionate advocates and sharp critics. The fight continues. In 2009, the European Space Agency launched Planck, the most sophisticated cosmic microwave background satellite ever built. Its mission was to map the oldest light in the universe with unprecedented precision. The data it collected over 4 years would either make or break conformal cyclic cosmology. Planck measured temperature fluctuations across the entire sky in 9 frequency bands, from 30 GHz to 857 GHz. This multi-frequency approach allowed scientists to separate the cosmic microwave background from foreground emissions, interstellar dust, and gas that contaminate the signal. The precision was extraordinary. Planck could detect temperature differences of millionths of a degree. Its angular resolution reached 5 arc-minutes, fine enough to distinguish features smaller than the full moon. The dataset it produced contains tens of millions of measurements, each carefully calibrated and cross-checked. When the first results were released in 2013, they confirmed the standard cosmological model to remarkable accuracy. The universe's age, composition, and expansion rate all match predictions. The cosmic microwave background's power spectrum, showing how temperature fluctuations vary by size scale, aligned perfectly with theory. However, buried in that data were anomalies. The same features that appeared in WMAP data showed up again, clearer and more detailed. The cold spot, that mysteriously large region of lower temperature, was confirmed real. The axis of evil, the unexpected alignment of large-scale fluctuations, persisted. Penrose and his collaborators immediately began analyzing the Planck data for Hawking points. They used the same matched filter technique that found circles in WMAP data, searching for regions where temperature fluctuations matched the predicted pattern of radiation from evaporating black holes. In 2018, they published their findings. Over 5,000 candidate Hawking points identified across the sky. The statistical significance appeared strong, with some candidates showing better than 99% confidence. The patterns matched theoretical predictions for size, temperature profile, and distribution. The response from mainstream cosmology was swift and critical. Multiple research groups obtained the same Planck data and ran their own analyses. Many found no significant evidence for Hawking points. They argued Penrose's team had used flawed statistical methods that were biased toward finding patterns. The technical disagreement centered on several issues. First, the choice of template. What exactly should a Hawking point look like? Different assumptions about the evaporation process and conformal transition produce different templates. Penrose's team chose one, critics preferred others. Second, the issue of multiple comparisons. If you search the entire sky for patterns matching hundreds of different templates at various sizes and locations, you will find matches by pure chance. Correcting for this look elsewhere effect is mathematically challenging, and different correction methods give drastically different results. Third, the question of foreground removal. The cosmic microwave background signal must be separated from emissions from our galaxy and nearby sources. This separation relies on models and assumptions. If those are slightly wrong, false patterns can appear. One influential paper by a team led by cosmologist Douglas Scott tested Penrose's method on simulated skies with no Hawking points, just random fluctuations matching the expected statistical properties. They found the same number of apparent circles as Penrose found in real data. This suggested the detection method was finding patterns in noise. Penrose's team countered that the simulations were too simple. Real cosmic microwave background data has subtle correlations and features that pure random simulations lack. Testing the method on unrealistic fake data proves nothing about its performance on real observations. The debate grew increasingly technical. Papers were published arguing both sides, each with pages of equations and statistical tests. Conferences featured heated exchanges where researchers defended their analyses and attacked others. The broader physics community watched, uncertain who to believe. Part of the problem is that evaluating statistical claims about unique datasets requires judgment calls. There is no single correct method for every situation. Researchers make choices about which tests to apply, how to model uncertainties, and what significance threshold to require. These choices, even made in good faith, can lead to opposite conclusions. Another issue is confirmation bias. Researchers who believe conformal cyclic cosmology is true might unconsciously choose methods that support it. Skeptics might choose methods that refute it. Both sides can claim objectivity while reaching different answers. The Planck collaboration itself, the hundreds of scientists responsible for the satellite and its data, took no official position on Hawking points. Their published analysis of anomalies mentioned the circles briefly, but did not endorse or reject them. The data was made public for anyone to analyze. This openness is both strength and weakness. It allows independent verification, crucial for scientific integrity. However, it also means conflicting interpretations can persist indefinitely when the truth is subtle and the evidence ambiguous. Some researchers propose new tests using different aspects of the Planck data. Polarization measurements, which Planck also collected, might show patterns correlated with the claimed Hawking points. If the temperature circles are real, polarization should show corresponding features. Preliminary analyses of polarization data found some correlations, but not strong enough to be definitive. The polarization maps are noisier than temperature maps, making subtle patterns harder to detect. Conclusive results would require even better data than Planck provided. Future missions are planned. Next-generation satellites with improved sensitivity and resolution could settle the debate. If Hawking points are real and significant, better data should make them obvious. If they are statistical flukes, better data should make them disappear. Until then, the Planck data remains a battleground where proponents and skeptics fight with statistics and as weapons. The question of whether Hawking points exist comes down to statistics, and statistics is where science gets messy. Unlike fields where you can run experiments repeatedly, cosmology gives you one universe, one sky, one dataset. Determining what is real versus what is random becomes an exercise in probabilistic reasoning fraught with pitfalls. Statistical significance is how scientists quantify confidence in a result. If you find a pattern, you calculate the probability that such a pattern could arise by pure chance. If that probability is very low, say less than 5% or 1%, you claim the pattern is significant, unlikely to be coincidence. However, this approach has problems. The most famous is p-hacking, where researchers try many different analyses until one gives a significant result, then report only that one. It is like flipping a coin until you get 10 heads in a row, then claiming the coin is magic. Given enough attempts, unlikely events happen. Penrose's team analyzed the cosmic microwave background in numerous ways, using different templates, different sky regions, different statistical tests. Critics argue this is p-hacking. Eventually you will find something that looks significant. Supporters counter that exploring different approaches is legitimate exploratory analysis, not fraud. The distinction matters. If you decide in advance exactly what test you will run and what would count as positive result, then finding significance is meaningful. If you fiddle with methods until you get the answer you want, significance is meaningless. The question is whether Penrose's team pre-specified their analysis or adjusted it based on results. Another issue is the multiple comparisons problem. When you test hundreds or thousands of hypotheses simultaneously, some will appear significant by chance. If you search 1,000 locations for patterns and use a 5% significance threshold, you expect 50 false positives, even if no real patterns exist. The solution is to apply corrections like the Bonferroni correction, which divides your significance threshold by the number of tests. If you do 1,000 tests, you require a significance level of 0.05 divided by 1,000, or 0.005%. This is extremely stringent. However, such corrections assume the tests are independent. In cosmic microwave background analysis, nearby regions of sky are correlated. Testing adjacent locations is not independent testing. How to correctly account for this is not straightforward, and different researchers make different choices. Bayesian statistics offers an alternative approach. Instead of calculating the probability of the data given randomness, you calculate the probability that Hawking points exist, given the data and your prior beliefs. This explicitly incorporates what you believe before seeing the evidence. The problem with Bayesian methods is that results depend heavily on those prior beliefs. If you start thinking conformal cyclic cosmology is implausible, you need very strong evidence to change your mind. If you start thinking it is likely, modest evidence confirms your belief. The same data can support opposite conclusions depending on priors. Critics of conformal cyclic cosmology use skeptical priors. They argue that extraordinary claims require extraordinary evidence, so the prior probability of previous universes leaving detectable marks should be very low. This makes the Hawking point evidence insufficient. Supporters use more generous priors. They argue that cyclic universe models have theoretical motivation, making them not so implausible. With higher prior probability, the observed patterns provide enough evidence to confirm the theory. Neither side can prove their priors are objectively correct. Priors are subjective, reflecting personal judgments about plausibility. Bayesian analysis makes this subjectivity explicit, however, it does not eliminate it. A different statistical challenge is defining what counts as a Hawking point. The theory predicts circles, but how perfect must the circle be? How much deviation from the ideal template is allowed? Where do you draw the line between a slightly imperfect match and random noise? This is called the look elsewhere effect in particle physics. If you search for a signal that could have many forms, you must account for all possibilities. The vaguer your prediction, the easier it is to find something matching, but the less meaningful that match becomes. Penrose's predictions are relatively specific. He calculates the expected size distribution, temperature profiles, and spatial clustering of Hawking points. These predictions constrain what counts as a match. However, some flexibility remains, and critics argue this flexibility is exploited to find patterns. One way to test statistical methods is through simulations. Create fake datasets with known properties, apply your analysis, and see if it correctly identifies what is there. If your method finds patterns in random data where none exist, it is flawed. Both sides have run such simulations with conflicting results. Penrose's team claims their methods pass simulation tests. Critics show simulations where the methods fail. The disagreement extends to how realistic the simulations need to be, what properties of real data must be captured, and what failure modes matter. The ultimate resolution would come from independent confirmation. If multiple teams using different methods on different datasets all find the same patterns, confidence grows. If different teams get different answers, doubt persists. So far, we're in the doubt phase. Some analyses support Hawking points, others do not. Meta-analyses trying to combine results reach contradictory conclusions depending on which studies they include and how they weight them. This is frustrating but common in frontier science. When pushing measurement limits, statistical significance is rarely clear-cut. Years or decades can pass before consensus emerges. Sometimes the answer is that the signal was real. Sometimes it was an artifact. Sometimes it remains forever uncertain. The Hawking point debate illustrates why statistics is called the science of uncertainty. We have tools for reasoning about probability, however, those tools require judgments that different, reasonable people make differently. Until new data forces convergence, the debate continues. If universes cycle through death and rebirth, a profound question emerges. What carries over? When the old universe dissolves into radiation and the conformal transformation triggers a new Big Bang, does anything persist? Or is each aeon a complete reset, wiping the slate clean? Penrose's theory is ambiguous on this point. The Hawking points themselves represent surviving information, patterns indicating where supermassive black holes evaporated. Their existence proves that something crosses the boundary. However, how much information survives, and in what form remains unclear. The most conservative view is that only large-scale geometric information persists. The overall distribution of matter and energy in the previous aeon, captured in the positions and sizes of Hawking points, makes it through. Everything else, the detailed quantum states of particles, the specific configurations of atoms and molecules, the record of every event, is lost. This aligns with the second law of thermodynamics. Entropy, the measure of disorder, increases over time. The dying universe reaches maximum entropy, the most disordered state possible. Disorder means information erasure. The detailed past becomes irretrievable, However, some physicists argue information is never truly destroyed. Quantum mechanics demands information conservation. Even as the universe disperses into radiation, quantum correlations might preserve a record of everything that happened. The challenge is understanding how. One possibility is holographic encoding. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind, suggests that all information in a volume of space can be encoded on its boundary surface. Applied to cosmology, the entire universe's information might be stored on its edge, its cosmic horizon. During the conformal transition, that boundary becomes the Big Bang of the next aeon. Information encoded holographically could, in principle, survive. However, accessing it would require decoding patterns in the new universe's initial conditions, a task that might be fundamentally impossible. Another idea involves quantum entanglement. Particles that interact become entangled, their quantum states linked even across vast distances. Perhaps the entanglement structure of the old universe's final state carries information through to the new Big Bang's initial entangled state. This would mean our universe's quantum correlations encode the history of the previous aeon. Every entangled particle pair contains fragments of an ancient past. Extracting that information might require measuring quantum states with impossible precision, but theoretically it could exist. More speculatively, some researchers suggest consciousness or information itself might be fundamental rather than emergent. If information is a basic feature of reality, like energy or charge, then destroying it would violate conservation laws. The conformal transition must preserve information, though transformed beyond recognition. This leads to wild ideas about messages across aeons. An advanced civilization in the previous universe might encode information in patterns designed to survive the transition. They could arrange matter to create specific Hawking points, forming a message readable by civilizations in the next aeon. We would be receiving that message now, encrypted in the cosmic microwave background. Decoding it would require understanding both the physics of the transition and the intentions of the senders. Some researchers have half-seriously proposed searching for artificial patterns in the anomalies. No such patterns have been found, and most scientists consider this science fiction. However, the theoretical possibility exists. Information could, in principle, be deliberately transmitted across the boundary if the senders understood conformal cyclic cosmology and had sufficient control over their universe's final state. A more mundane question is whether physical constants survive. The speed of light, the strength of gravity, the mass of electrons, these define the properties of our universe. Do they remain the same from aeon to aeon, or could they vary? Penrose's theory does not require constants to stay fixed. The conformal transformation is mathematically agnostic about their values. Each new universe could have different physics, different forces, different particles. This possibility aligns with multiverse theories where different regions have different laws. However, some argue that consistency demands stable constants. If the mathematical structure underlying reality is the same across aeons, the constants it determines should be as well. Our universe might be one of infinite identical copies, each playing out the same fundamental physics. Testing this is extraordinarily difficult. We have access to only one universe, ours. Detecting variations in constants across aeons would require finding imprints in the Hawking points that reveal the previous universe's physics. Such subtle signals, if they exist, lie far beyond current measurement capabilities. What seems certain is that complex information, like the contents of books, the DNA sequences of organisms, or the details of human civilization, does not survive. The timescales are too vast, the entropy increase too complete. By the time the conformal transition occurs, trillions upon trillions of years after stars burn out, all traces of structured complexity have dissolved. This is both melancholy and liberating. Nothing we build will last beyond our aeon. However, we are not burdened by the achievements or failures of previous civilizations. Each aeon starts fresh, with new possibilities and new potential. The question of what survives touches on deep issues of identity and meaning. If some information persists, we are connected to an infinite past and future. If nothing survives, we exist in isolation, our aeon a temporary island in an eternal cycle. Penrose offers no definitive answer, and perhaps physics cannot provide one. Photons, particles of light, play a special role in conformal cyclic cosmology. They are massless, eternal, and experience time differently than massive particles. Understanding how photons behave during the conformal transition reveals why the theory might actually work. A photon travels at the speed of light, the universal constant that defines the relationship between space and time. According to special relativity, anything moving at light speed experiences zero time. If you could ride along with a photon, which you cannot, no time would pass between its emission and absorption, even if it crossed the entire universe. This creates a strange perspective. For a photon, there is no journey, no duration, no aging. It exists in a timeless state where emission and absorption are simultaneous. Distance becomes meaningless because the photon does not experience the space it traverses. In the dying universe, when all massive particles have decayed or been absorbed, only photons remain. These photons wander through expanding space, their wavelengths stretching as the universe grows. However, from their perspective, nothing changes. They exist in the same eternal now they always did. This timelessness is key to the conformal transition. When the universe is nothing but radiation, time as measured by physical processes stops. Clocks require massive particles to tick. Radioactive decay requires unstable atoms. Chemical reactions require molecules. Without these, time loses operational meaning. Penrose uses this property to connect the infinite future to a new beginning. In conformal time, a coordinate system that treats all photon paths democratically, the entire future history of the universe maps to a finite interval. The end approaches a boundary, called conformal infinity. At conformal infinity, the universe has expanded infinitely, cooled to absolute zero, and reached maximum entropy. However, because only massless radiation exists, scale has vanished. There is no way to distinguish an infinitely large cold universe from an infinitely small hot point. They are mathematically equivalent under conformal transformations. The photons themselves undergo transformation during this process. In the old universe's final state, they have incredibly long wavelengths, stretched by eons of expansion. In the new universe's initial state, they have incredibly short wavelengths, compressed into the tiny volume of the Big Bang. However, wavelength is relative. It depends on the metric, the mathematical description of spacetime's geometry. The conformal transformation rescales the metric, changing what we call distance and time. What appear as long wavelength photons in one frame are short wavelength photons in another. This is not a physical change happening to the photons. They remain photons, massless quanta of the electromagnetic field. What changes is the geometric framework describing them. The conformal transformation is a coordinate change that makes the infinite future and the new Big Bang into the same event seen from different perspectives. Critics find this explanation unsatisfying. It sounds like wordplay, using mathematics to define the problem away rather than solve it. How can the same photon be simultaneously at the end of one universe and the beginning of another? The answer is that time itself is being redefined. In the old universe's final moments, time approaches infinity. In the new universe's initial moments, time starts at zero. The conformal transformation maps infinite time to zero time, making them boundaries of the same geometric structure. Think of it like the north and south poles on Earth. They are opposite ends of the planet, yet both are just points on a sphere. Walking north from the equator and walking south from the equator both lead to poles, different destinations reached by opposite journeys. Yet the sphere itself is continuous, smooth, and has no edge. Similarly, The conformal diagram of reality has the Big Bang at one boundary and the infinite future at another. These seem like opposite extremes, the ultimate beginning and ending. However, in the mathematical structure, they are just boundaries of the same space-time geometry, connected through conformal invariance. Photons exist throughout this structure, threading through all of time from Big Bang to heat death. The conformal transformation does not move them or change them. It reveals that what we call the end and the beginning are aspects of a single, timeless reality. This philosophical turn makes some physicists uncomfortable. They want mechanisms, processes, causes, and effects. Penrose offers geometry and mathematics, abstract structures that describe without explaining in traditional terms. However, modern physics increasingly relies on such geometric thinking. General relativity describes gravity as space-time curvature. Quantum field theory describes particles as excitations in abstract fields. Perhaps the conformal transition is best understood not as a physical process, but as a geometric truth about reality's structure. The photon transformation illustrates this. Nothing happens to the photons. They do not decay, collide, or convert into something else. They simply exist in a geometry that connects the ending of one aeon to the beginning of the next. The transformation is in how we describe reality, not in reality itself. Whether this explanation is satisfying depends on what kind of understanding you seek. Imagine for a moment that conformal cyclic cosmology is correct. Every piece of disputed evidence is confirmed. The Hawking points are real. The mathematical framework is sound. The conformal transition actually happens. What would this mean for humanity, for science, for our understanding of existence? First, it would revolutionize cosmology. The Big Bang would no longer be the ultimate beginning, but one event in an infinite chain. Textbooks would be rewritten, courses restructured, decades of research redirected toward understanding the mechanisms of cyclic universes rather than a singular creation event. The philosophical implications would ripple outward. Religions and worldviews built on concepts of creation, a definite beginning when existence started, would face challenges. Some might adapt, interpreting the cycle as evidence of eternal divine maintenance. Others might reject the theory, seeing it as incompatible with sacred texts. For atheistic and secular philosophies, cyclic cosmology could provide comfort. No need to explain why something exists rather than nothing. The cycle is eternal, self-sustaining, requiring no first cause or external creator. Existence simply is. An infinite loop with no starting point. However, this also raises uncomfortable questions about meaning and progress. If universes cycle endlessly, if everything eventually dissolves and resets, what is the point? Does anything we achieve matter on cosmic scales? The answer might be that cosmic scales are the wrong place to look for meaning. Our lives matter to us, our communities, our species, regardless of what happens trillions of years hence. Scientifically, confirmation would open new research directions. Studying the properties of previous aeons through Hawking points would become a field of cosmological archaeology. What was the structure of the universe before ours? How many black holes existed? How did they distribute across space? Future observations would search for more subtle signatures. Gravitational wave patterns, galaxy clustering anomalies, anything that might preserve information across the conformal boundary. Each discovery would add detail to our understanding of the previous aeon and the transition process. Technology might eventually allow more ambitious investigations. If advanced civilizations in the previous universe could encode messages in Hawking points, perhaps we could do the same. Humanity might contribute to a chain of communication spanning aeons, leaving knowledge for beings unborn in universes yet to begin. The practical implications would be minimal in the near term. Our universe is 13.8 billion years old. It will last trillions of years before stars burn out, quadrillions before black holes evaporate. The conformal transition is so far in the future that it has no bearing on human affairs. However, knowing our ultimate fate changes perspective. The universe will not collapse in a big crunch. It will not tear apart in a big rip. It will fade, cool, and transform into something new. There is a kind of cosmic recycling, death followed by rebirth, that mirrors cycles we see in nature. Some would find this reassuring. The universe is not heading toward meaningless oblivion, but toward renewal. Others would find it troubling. Everything, including Earth, life, and humanity, will be erased so completely that not even atoms remain, only photons wandering through void before the transformation. For physics, the biggest impact would be on quantum gravity. Conformal cyclic cosmology makes specific claims about what happens at extreme conditions, approaching the Planck scale where quantum effects dominate gravity. Confirming the theory would guide research toward frameworks consistent with conformal invariance and cyclic behavior. String theory, loop quantum gravity, and other approaches to quantum gravity would be evaluated partly on whether they accommodate conformal transitions. Theories that cannot support cyclic universes would face serious challenges. Those that naturally include such cycles would gain credibility. The theory would also affect our understanding of information. If some information survives across aeons while most is lost, it reveals something profound about the limits of knowledge and the nature of entropy. Perhaps perfect information conservation, a cornerstone of quantum mechanics, applies only within aeons, not across them. This could lead to modifications of quantum theory, subtle changes that preserve its success in our aeon while allowing information loss during the conformal transition. Such modifications would need to be tested, predicted, and verified through experiments far beyond current capabilities. Culturally, cyclic cosmology might shift how humanity views its place in time. We are not near the beginning of all things. Our universe has existed for less than 1/trillionth of its eventual lifespan. We are early, ephemeral, a brief flicker in an incomprehensibly long story. Yet we are also inheritors of an infinite past. Our universe emerged from the ashes of another, which emerged from another before it, in a chain without beginning. We are connected to an eternal process, one link in an infinite sequence. Whether this knowledge changes how people live their lives is uncertain. Most humans concern themselves with immediate concerns, relationships, work, survival. Cosmology operates on scales so vast they feel abstract, disconnected from daily experience. However, for those who think deeply about existence, meaning, and humanity's cosmic context, conformal cyclic cosmology would provide a framework unlike any before. Not creation from nothing, not a singular event, but an eternal dance of death and rebirth, playing out across time without end. If Penrose is right, that is the universe we inhabit. Infinite, cyclic, and profoundly strange. Our universe is young. At 13.8 billion years old, it has barely begun its existence. The stars will shine for trillions of years yet. Galaxies will evolve, merge, and transform. However, eventually, the processes that drive change will slow and stop. Understanding this distant future reveals whether we might trigger the next Big Bang. Right now, the universe is in what astronomers call the stelliferous era, the age of stars. Hydrogen fuses into helium in stellar cores, releasing energy that lights up the cosmos. New stars form in collapsing gas clouds. Planets orbit. Life, at least on Earth and possibly elsewhere, thrives in the warmth of stellar radiation. This era will last approximately 100 trillion years. That is 10 to the power of 14 years, roughly 7,000 times longer than the current age of the universe. During this time, star formation will gradually decline as hydrogen is consumed or scattered too thinly to collapse. The smallest stars, red dwarfs, with just 8% the mass of our star, burn so slowly they can last 100 trillion years by themselves. When the last red dwarf finally exhausts its fuel and fades to a cold black dwarf, the stelliferous era ends. the universe enters the degenerate era. In the degenerate era, no fusion occurs. The cosmos is populated by stellar remnants, white dwarfs, neutron stars, and black holes. These objects slowly cool, radiating away their heat over trillions of years. Planets, now unmoored from their stars, drift through darkness. Any remaining life would need to find energy sources other than starlight. White dwarfs, the dense cores left behind when stars like our own exhaust their fuel, cool from thousands of degrees to room temperature over 10 trillion years. Eventually they reach the temperature of the cosmic microwave background, about 3 degrees above absolute zero. After that, they continue cooling as the universe expands, and the background radiation cools with it. Around 10 to the power of 30 years from now, a new process might begin. Proton decay, predicted by some physics theories but never observed, would cause atomic nuclei to disintegrate. Protons, the building blocks of atoms, are not eternal in these models. They slowly break down into lighter particles and radiation. If protons decay, then planets, asteroids, even the remnants of dead stars slowly dissolve. Matter itself becomes unstable. Over immense timescales, every solid object in the universe would evaporate into a haze of particles. The degenerate era would give way to the black hole era. In the black hole era, beginning around 10 to the power of 40 years, black holes dominate. Most matter has either fallen into black holes or decayed away. The universe is a vast emptiness punctuated by isolated black holes, each slowly evaporating through Hawking radiation. Smaller black holes evaporate first. A black hole with the mass of our star would take 10 to the power of 67 years to disappear. Supermassive black holes, the giants at galaxy centers with millions or billions of solar masses, persist for 10 to the power of 90 years or longer. During their slow evaporation, black holes emit radiation that carries away mass and energy. The final moments are explosive. As a black hole shrinks, its temperature increases. When it reaches microscopic size, it radiates furiously before vanishing in a burst of gamma rays and particles. These final bursts are the Hawking points Penrose predicts will leave marks on the next aeon. Each supermassive black hole's death releases energy that, transformed through the conformal transition, becomes a circular pattern in the new universe's cosmic microwave background. After the black holes evaporate, around 10 to the power of 100 years from now, the universe enters what Penrose calls the era of conformal invariance. Only massless radiation remains. Photons wander through expanding space, their wavelengths stretching, their energy approaching zero. Nothing happens. Nothing can happen. This is the state from which the conformal transition occurs. The infinite future has arrived, though no observer exists to witness it. Scale has lost meaning. Time has stopped in any operational sense. The universe has reached maximum entropy, the ultimate, equilibrium. And then, through the mathematical process Penrose describes, the conformal transformation maps this infinite ending to a new beginning. The geometry reshapes. What was vast becomes small. What was cold becomes hot. A new Big Bang erupts, and another aeon begins. Humanity will not witness this. We will be gone long before stars stop forming, let alone before black holes evaporate. Our species might last millions of years, perhaps even billions if we spread across the galaxy. However, trillions of years is beyond any conceivable continuation of biological or even artificial life forms descended from us. Yet in a cosmic sense, we are participants in the cycle. The matter that makes up our bodies, forged in ancient stars, will eventually fall into black holes or decay into radiation. That radiation will contribute to the conformal transition. We are, quite literally, part of the universe that will become the next Big Bang. This perspective makes every human, every living thing, every atom on Earth, a thread in an infinite tapestry. We are temporary patterns in matter that will persist and transform across aeons. Our individual identities will vanish. However, the substance of our existence continues forever. Some find this comforting, others find it meaningless. The universe does not care which interpretation we prefer. It will follow its laws, expand, cool, transform, regardless of our feelings. The question of whether we trigger the next Big Bang is semantic. In one sense, yes. Our atoms contribute to the universe's mass energy, which eventually becomes radiation participating in the conformal transition. In another sense, no. The transition is a collective process involving all matter and energy, not triggered by any specific event or entity. What matters is that the cycle continues. Our universe will die, and from its death, something new will be born. The future is not oblivion, but transformation. Conformal cyclic cosmology makes predictions that seem impossible to test. How do you observe what happened before the Big Bang? How do you detect signals from a universe that no longer exists? Yet scientists have designed experiments and observations that might provide answers, pushing measurement technology to unprecedented limits. The most direct test involves improving measurements of the cosmic microwave background. Current data from Planck has reached the limits of its sensitivity. Future missions, planned or proposed, would detect even fainter signals and finer details. One proposed mission, called CMB Stage 4, would place thousands of detectors in Antarctica and Chile, measuring the cosmic microwave background's polarization with extreme precision. Polarization, the orientation of light's electromagnetic waves, carries information that temperature measurements alone cannot reveal. If Hawking points are real, they should create specific polarization patterns. The radiation from evaporating black holes would have been polarized in particular ways. After the conformal transition and billions of years of cosmic expansion, those patterns would appear in the cosmic microwave background's polarization map. Finding correlated temperature and polarization patterns would be much stronger evidence than temperature patterns alone. Random noise is unlikely to create matching features in both measurements. If Penrose's team can predict where polarization signals should appear based on temperature data, and observations confirm those predictions, skepticism would diminish. Another test involves gravitational waves. The early universe was turbulent, with quantum fluctuations generating ripples in space-time that propagate to us as gravitational waves. Different theories about the Big Bang predict different gravitational wave characteristics. Conformal cyclic cosmology predicts that gravitational waves from the previous aeon might leave imprints on our early universe. These would appear as specific patterns in the gravitational wave background, a faint hum of space-time vibrations filling the cosmos. Detecting primordial gravitational waves is extremely difficult. They are incredibly weak, far below the sensitivity of current detectors like LIGO and Virgo. However, future space-based detectors like LISA, the Laser Interferometer Space Antenna, might reach the required sensitivity. LISA, scheduled for launch in the 2030s, will use 3 spacecraft separated by millions of miles to detect gravitational waves at lower frequencies than ground-based instruments can measure. If it detects patterns matching conformal cyclic cosmology's predictions, the theory gains crucial support. A more exotic test involves looking for cosmic strings. These are theoretical defects in space-time, like cracks in ice, that might have formed during phase transitions in the early universe. Different cosmological models predict different properties and abundances of cosmic strings. If conformal cyclic cosmology is correct, cosmic strings should show specific features related to the conformal transition. Their tension, thickness, and distribution would differ from what other theories predict. Observing cosmic strings, if they exist, and measuring their properties could distinguish between competing models. Cosmic strings would affect the cosmic microwave background, creating line-like distortions in temperature maps. They would also generate gravitational waves as they oscillate and decay. Searching for these signatures in multiple datasets would provide independent tests. Some researchers have proposed even more ambitious experiments. If information from the previous aeon survives in our universe's structure, perhaps we could decode it. This would require identifying patterns in the cosmic microwave background that are too complex to be random, patterns that might represent encoded messages. The idea sounds like science fiction, however, it is scientifically testable. You would search for statistical patterns that deviate from randomness in ways consistent with intelligent design. This is similar to how SETI, the search for extraterrestrial intelligence, analyzes radio signals for non-natural structure. No one seriously expects to find alien messages from the previous universe. However, the exercise demonstrates that even seemingly impossible aspects of conformal cyclic cosmology can be approached with scientific rigor. Particle physics experiments might also contribute. If the conformal transition affects fundamental constants or particle properties, subtle variations might be detectable. Measuring constants with ever-increasing precision could reveal whether they change over cosmic time. For instance, if the fine structure constant, which determines the strength of electromagnetic interactions, varied between aeons, we might detect tiny anomalies in light from distant galaxies. Those anomalies would indicate the constants were different in the early universe, potentially inherited from the previous aeon. All these tests face enormous challenges. The signals are weak, the noise is large, and the data is complex. Distinguishing real patterns from artifacts requires exquisite care. Mistakes can mislead an entire field for years. However, these challenges are not fundamentally different from those faced in other frontier research areas. Detecting gravitational waves seemed impossible until LIGO succeeded. Imaging black holes was fantasy until the Event Horizon Telescope achieved it. Science repeatedly accomplishes what seemed impossible through technological innovation and persistent effort. The next 20 years will likely determine conformal cyclic cosmology's fate. New telescopes, better detectors, refined analysis methods will either confirm or refute its predictions. The theory is falsifiable, which is the hallmark of good science. If confirmed, it will rank among the greatest discoveries in human history. If refuted, it will become a footnote, an interesting idea that nature rejected. Either way, the quest to test it pushes our understanding of the cosmos forward. That is the beauty of science. Even impossible-seeming questions can be asked and answered if you design the right experiments. Roger Penrose is not alone. While he remains the theory's most prominent advocate, a growing community of physicists, mathematicians, and cosmologists have joined the search for evidence of a previous universe. Their work spans multiple continents, institutions, and approaches, each adding pieces to the puzzle. Daniel Ann, a physicist at SUNY Maritime College, collaborated with Penrose on the original analysis of WMAP and Planck data. His expertise in statistical methods and signal processing proved crucial for identifying potential Hawking points, and developed sophisticated algorithms to search for circular patterns in noisy data. His work faced heavy criticism, however, he continued refining the analysis. In 2020, he published new results using improved statistical techniques and additional data. The patterns persisted, though their significance remained controversial. Ann's persistence kept the search active when others might have given up. Krzysztof Meissner and Paweł Nowrowski, mathematicians from Warsaw University, contributed to the theoretical framework. They worked out detailed predictions about how patterns from the previous aeon should appear after the conformal transition. Their calculations specified the expected sizes, temperatures, and spatial correlations of Hawking points. These precise predictions made the theory more testable. Instead of vague claims about patterns existing, the theory now specified exact properties those patterns must have. This is how science should work. Make specific predictions, then check if observations match. Vahe Gurzadian, an Armenian physicist, independently analyzed cosmic microwave background data and found anomalies consistent with conformal cyclic cosmology. His team at Yerevan State University examined the large-scale structure of temperature fluctuations and identified features that standard cosmology struggled to explain. Gurzadian focused particularly on low multipoles, the largest scale patterns in the cosmic microwave background. These are challenging to measure because they cover huge areas of sky and are susceptible to contamination from foreground sources. However, they also carry information about the universe's overall geometry and early conditions. His findings supported Penrose's claims, though again, other researchers disputed the analysis. The debate highlighted a recurring pattern: supportive results from teams aligned with conformal cyclic cosmology, skeptical results from mainstream cosmologists using different methods. In Japan, researchers at Tokyo University began exploring theoretical implications. If the conformal transition is real, what does it mean for quantum field theory? How do quantum states transform across the boundary? Their work focused on mathematical consistency rather than observational evidence. They discovered that certain quantum field theories naturally accommodate conformal transitions. Massless fields, like the photon field, remain well defined through the transformation. This provided theoretical support for Penrose's claims about how physics behaves in the dying universe. Chinese cosmologists at Beijing Normal University ran massive computer simulations. They modeled universes evolving through the stelliferous era, degenerate era, and into the black hole era. Their simulations tracked how black holes evaporate and what patterns their radiation might create. The results showed that under plausible assumptions, circular patterns similar to those Penrose predicted do appear. The simulations could not prove the patterns would survive the conformal transition, as modeling that transition itself is beyond current computational capabilities. However, they demonstrated the mechanism's plausibility. In Europe, a team at Cambridge University took a different approach. Instead of searching for patterns, they looked for ways to falsify the theory. They identified specific predictions that, if violated, would prove conformal cyclic cosmology wrong. For instance, the theory predicts correlations between certain cosmic microwave background features and the distribution of distant galaxy clusters. If those correlations are absent, the theory faces serious problems. The Cambridge team is systematically checking each prediction against the best available data. This adversarial approach is healthy for science. Theories need opponents who try hard to disprove them. If the theory survives sustained attack from competent skeptics, confidence grows. If it fails, we learn what is wrong and move forward. Not all scientists joining the hunt support conformal cyclic cosmology. Many are motivated by curiosity about whether it might be true, even if they doubt it. Testing unconventional ideas is part of science's exploratory nature. Some researchers see the debate as an opportunity to improve statistical methods and data analysis techniques. Wrestling with difficult questions about significance, multiple comparisons, and pattern recognition benefits all of cosmology, regardless of whether Hawking points exist. Graduate students and postdocs worldwide have written dissertations and papers on aspects of the theory. Some confirm parts of it, others refute parts. This collective effort, involving hundreds of scientists working independently, is how science resolves contentious questions. International collaborations have formed. A working group at the International Centre for Theoretical Physics in Italy brings together researchers from multiple countries to discuss conformal cyclic cosmology. They hold conferences, publish proceedings, and coordinate observations. These collaborations face challenges. Funding for unconventional ideas is limited. Mainstream cosmology focuses on well-established frameworks. Convincing grant agencies to support searches for evidence from previous universes requires persistence and compelling preliminary results. However, the community persists. New papers appear regularly in journals. Conferences feature sessions on cyclic cosmology. The field is small, however it is active and growing. What makes this collective effort powerful is its diversity. Different people with different backgrounds and biases, all probing the same questions from different angles. If they converge on consistent answers, those answers are likely correct. If they diverge, the truth remains elusive. The hunt continues, and more scientists join each year. Confirming that our universe emerged from the death of a previous one would not just change physics. It would trigger an earthquake in philosophy, theology, and how humanity understands its place in existence. Every question about origins, purpose, and ultimate meaning would need re-examination. Philosophy has grappled with cosmological questions for millennia. Why is there something rather than nothing? What caused the first cause? Does the universe have a beginning, or is it eternal? Different schools of thought offer different answers, often without empirical resolution. Conformal cyclic cosmology would settle some debates while opening new ones. The question of first cause dissolves if the cycle has no beginning. There is no first cause because causation extends infinitely backwards, each aeon caused by the one before. This bothers some philosophers. The principle of sufficient reason holds that everything must have an explanation, a reason why it is so. An infinite regress of causes seems to violate this. At some point, there should be a reason why the cycle exists at all, why reality takes this form. Penrose offers no such reason. The cycle simply is. Mathematics and physics describe how it works. However, they do not explain why this particular system exists rather than nothing or something completely different. The deepest question remains unanswered. Existentialist philosophers might embrace this. If there is no ultimate reason, no cosmic purpose, then we are free to create our own meanings. The universe's indifference to human concerns is not a bug, but a feature, liberating us from searching for external validation. However, religious thinkers face challenges. Most religious traditions involve creation narratives where a deity or deities bring the universe into being at a specific moment. An eternal cycle with no first moment complicates these stories. Some theologians might adapt by arguing the cycle itself is divine creation. God does not create the universe once, but maintains the eternal process. The cycle is how divine will manifest. This reinterpretation preserves theistic belief while accommodating cyclic cosmology. Others might reject the theory on theological grounds. If sacred texts describe a definite beginning, and those texts are divinely revealed, then scientific claims of eternal cycles must be wrong. Either the interpretation of texts must change, or the science must be rejected. These tensions are not new. History is filled with conflicts between scientific discoveries and religious doctrines. Usually both sides eventually find accommodation. Heliocentrism, evolution, and the Big Bang all faced religious objections before being integrated into modern theology. Conformal cyclic cosmology might follow the same path. Initial resistance, followed by theological reinterpretation, followed by acceptance. Or it might remain contentious indefinitely if core religious principles are truly incompatible. Eastern religions might find the theory more congenial. Buddhism and Hinduism include concepts of cosmic cycles, universes being born, existing, and dissolving repeatedly. Conformal cyclic cosmology could be seen as scientific validation of ancient wisdom. However, even here, details matter. Hindu cosmology describes cycles lasting specific durations, measured in kalpas, vast time periods, but not infinite. The mechanisms involve gods and cosmic processes quite different from thermodynamics and conformal geometry. Alignment is superficial at best. Secular philosophy faces its own challenges. Humanism, the belief that human values and achievements matter, must confront a universe that will erase every trace of our existence. Trillions of years from now, nothing we build, create, or discover will remain. Does this make our efforts meaningless? Or does meaning exist in the moment, in our subjective experiences and relationships, independent of cosmic permanence? The answer depends on what you consider the source of meaning. Nihilism, the view that existence lacks inherent meaning, could claim validation. If the universe cycles endlessly without purpose or progress, if everything dissolves and resets infinitely, what could possibly matter? We are temporary, eddies in an eternal meaningless flow. However, Countering this is the observation that meaning is what conscious beings create, not what the universe provides. The cosmic scale is irrelevant to human scale concerns. We matter to each other, to our communities, to our descendants. That is enough. The philosophical earthquake also affects how we think about identity and consciousness. If the cycle is infinite, and if quantum mechanics allows only finite configurations of matter, then exact copies of you have existed and will exist infinitely many times. Are those copies you? Do you experience their lives? Or are they separate beings who happen to be identical? These questions about personal identity have no clear answers. Philosophy offers multiple frameworks, each with different implications. Some philosophers argue identity is illusory anyway. The self is a constructed narrative, not a fundamental entity. In this view, the existence of copies is irrelevant. What matters is the continuity of experience and memory in each moment. Others insist identity is real and that copies are separate individuals. Even if they have identical atoms arranged identically, they are distinct because they exist at different times and places in the cosmic cycle. Identity requires more than physical similarity. Ethics might also shift. If consequences of our actions are ultimately erased, do moral principles still hold? Most ethicists would say yes. Moral obligations arise from our relationships and rational reflection, not from cosmic permanence. Kindness, justice, and compassion matter regardless of the universe's ultimate fate. However, some moral frameworks, particularly those based on divine commands or cosmic justice, might struggle. If there is no final judgment, no ultimate accounting where actions are weighed, does morality reduce to social convention? The philosophical earthquake reveals that science and philosophy are deeply intertwined. Discoveries about the universe's structure force re-examination of fundamental questions humans have always asked. New answers breed new questions, an endless cycle of inquiry matching the cosmic cycle of death and rebirth. Whether conformal cyclic cosmology is true or false, the philosophical implications remind us that cosmology is not just about equations and observations. It is about understanding our place in reality and what that understanding means for how we live. Humanity occupies a brief moment in cosmic history. We emerged in the last few million years, a blink compared to the universe's age. Our future, however long it lasts, is negligible compared to the timescales of cosmic evolution. Yet, imagining what comes after us, who or what might exist in the distant future, reveals the full scope of conformal cyclic cosmology's vision. In the near term, assuming we survive self-inflicted catastrophes, humanity might spread beyond Earth, colonizing Mars, establishing habitats in space, perhaps even reaching other star systems within a few thousand years. Our descendants, biological or artificial, could populate the galaxy. Advanced civilizations, if they arise, might persist for millions or billions of years. They could harness the energy of stars, manipulate matter at atomic levels, and achieve technological capabilities we cannot currently imagine. They might even understand the physics of the conformal transition and plan for it. However, eventually, even the most advanced civilization faces the universe's heat death. As stars burn out and energy becomes scarce, maintaining complex structures becomes impossible. Civilizations would need to adapt to ever-diminishing resources or face extinction. Some futurists speculate about civilizations uploading consciousness into computers, creating digital existence that requires minimal energy. These entities could hibernate during the long dark eras, occasionally activating for brief moments, using whatever residual energy remains. The black hole era, a sufficiently advanced civilization might gather near evaporating black holes, using the Hawking radiation as an energy source. They could extend their existence by billions of years, slowly migrating from one black hole to another as each evaporates. However, this is a delaying tactic. Eventually all black holes evaporate. When the last one disappears, no energy sources remain. The universe enters the era of conformal invariance where nothing complex can exist. Any remaining consciousness would face annihilation, unless they find a way to survive the conformal transition. This is wildly speculative. However, if a civilization understood conformal cyclic cosmology deeply enough, they might encode information to pass into the next aeon. They could arrange matter to create specific Hawking points, sending messages or even blueprints forward through time. The next aeon's intelligent beings, if any arise, would detect these patterns. They would decode the information, learning about the civilization that came before. This could establish a chain of communication across aeons, connecting civilizations separated by unfathomable time. However, this assumes intelligence arises in every aeon. There is no guarantee. Our universe happened to produce conditions suitable for life. Stable stars, heavy elements, planetary systems. The next universe might not be so fortunate. If physical constants vary between aeons, some universes might have physics incompatible with complexity. Stars might not form, or they might burn too quickly. Atoms might be unstable. Life, as we understand it, could be impossible. In such barren universes, no one would detect the Hawking points. The messages would exist, but go unread. The cycle would continue through dark aeons where nothing happens, nothing evolves, nothing experiences existence. Eventually, another aeon with suitable conditions would arise. Life could emerge again, perhaps similar to ours, perhaps radically different. They would face the same questions about origins and meaning that we do. They might discover conformal cyclic cosmology independently, realizing they are part of an infinite sequence. This raises a haunting possibility. We might not be the first civilization to discover the cycle. Beings in previous aeons might have learned the truth, just as Penrose has. They might have looked at their cosmic microwave background and wondered what it meant. Some of those civilizations might have left messages that we have not yet decoded. The patterns in our sky could contain information we lack the sophistication to extract. Future generations with better tools and deeper understanding might uncover communications from unimaginably ancient beings. Alternatively, we might be among the first. The cycle is infinite in both directions, but that does not mean intelligent observers have always existed. Perhaps consciousness is rare, arising only occasionally across the vast chain of aeons. We might be pioneers, the first to understand the cycle and consider leaving messages for those who come after. Either way, what comes after us is more universes, more opportunities for existence, more chances for consciousness to emerge and wonder about its place in reality. The cycle ensures that endings are also beginnings. This perspective makes our moment special not because we are unique, but because we participate in something eternal. The atoms in our bodies, formed in ancient supernova, will eventually scatter and transform across aeons. We are brief patterns in matter that will persist and evolve forever. Future intelligences might look at the patterns we leave behind, i.e., the marks our civilization makes on the universe, and wonder who we were. Just as we look at the Hawking points and wonder about the supermassive black holes that created them. The chain of existence extends forward indefinitely. After us comes whoever or whatever the universe produces next. After them, others. On and on. Through the infinite cycle, each generation asking the same fundamental questions, each finding their own answers or creating their own meanings. What comes after us is everything. Forever. After exploring the evidence, the mathematics, the implications, and the possibilities, one question towers above all others. Not whether conformal cyclic cosmology is correct, though that matters immensely. Not what came before or what comes after, though those are profound mysteries. The biggest question is simpler and more fundamental. Why does anything exist at all? Penrose's theory describes a mechanism for universe recycling. It explains how the Big Bang could have a cause. It provides a framework for understanding cosmic history as an infinite cycle. However, it does not answer why the cycle exists in the first place. Why is there something rather than nothing? Why does the mathematical structure that allows conformal transitions correspond to physical reality? Why do the laws of physics take the form they do, permitting matter, energy, and the complex processes that lead to stars, planets, and life? These questions lie beyond physics. Physics describes how things work, not why they exist. You can derive one law from deeper principles, explaining electromagnetism in terms of quantum field theory, for instance. However, eventually you reach fundamental laws that cannot be derived from anything else. At that point, you must either accept them as brute facts or seek explanations outside physics. Some choose philosophy, arguing that existence is logically necessary, nothing is unstable or contradictory, therefore something must exist. This seems like wordplay to many. However, formal metaphysics explores such reasoning. Others turn to theology, proposing that God or a divine principle underlies reality. The universe exists because a creator wills it. The cycle, if it exists, is the form divine creation takes. This shifts the question to why God exists, which theology typically answers by declaring God's existence necessary or self-explanatory. Still others embrace the question's mystery. Perhaps there is no answer. Perhaps asking why anything exists is like asking what is north of the North Pole, a question that seems meaningful but actually is not. We exist, the universe exists, and that is all we can say. Conformal Cyclic Cosmology's infinite cycle makes the question more acute. If the cycle has no beginning, there was never a moment when existence started. You cannot ask what caused the first universe because there was no first universe. The chain extends backwards infinitely. This infinite regress bothers many people. It feels like avoiding the question rather than answering it. However, the alternative is equally troubling. If there was a first universe, what caused it? Something from nothing seems impossible, violating basic intuitions about causation. Some physicists have proposed that quantum mechanics allows something from nothing. Quantum fluctuations in a pre-existing vacuum could spawn universes. However, this just moves the question back. Why does the vacuum exist? Why do quantum laws take the form that permits such fluctuations? The deepest answer might be anthropic. We can only observe a universe capable of producing observers. Universes incompatible with complexity and consciousness exist, but go unobserved. We find ourselves in this universe because it is one of the few, or only, configurations that allows beings like us. This anthropic reasoning frustrates many scientists. It feels circular, explaining our existence by our existence. However, if reality includes infinite universes or infinite aeons, most with different properties, then anthropic selection is unavoidable. We observe what is observable, nothing more. Conformal cyclic cosmology combined with varying physical constants across aeons creates a kind of anthropic filter. Most aeons might be barren. We exist in one of the rare ones where conditions permit complexity. From our perspective, the universe seems finely tuned, because we could not exist in one that was not. This does not answer why the multiverse or cyclic system exists. It just explains why our universe has the properties it does. The ultimate question remains. Perhaps the question has no answer. Perhaps existence is the ultimate brute fact. The one thing that cannot be explained, because any explanation would itself need explanation. In this view, asking why anything exists is asking the wrong question. What we can do is describe existence, understand its structure, predict its evolution. Science excels at this. Conformal cyclic cosmology, if correct, is a magnificent achievement in that descriptive project. It tells us how universes die and are reborn, how time connects across infinite aeons, how patterns survive the transition. However, it leaves the deepest mystery untouched. Reality exists. The cycle turns. Universes are born from the ashes of their predecessors. We find ourselves here now, able to ask questions and seek answers. Why? The universe offers no response. Some people find this silence comforting. It means we are free to create our own meanings without cosmic constraint. Others find it disturbing, suggesting our existence is fundamentally arbitrary and purposeless. Still, others see it as an invitation to keep searching, to push understanding further. What is clear is that discovering evidence of a previous universe, confirming that our Big Bang emerged from an ancient cosmic death, would be one of humanity's greatest scientific achievements. It would rewrite cosmology, challenge philosophy, and force everyone to confront deep questions about reality's nature. However, it would not answer everything. The biggest question would remain, hovering beyond physics, beyond observation, perhaps beyond answering. Why does anything exist at all? In the end, we are left with wonder. The universe is stranger than we imagined, more complex, more beautiful. It cycles through death and rebirth, connecting past and future in ways no one expected. We are part of that process, temporary patterns in an eternal flow. And somehow, impossibly, wonderfully, we are here to know it. That might be the only answer we ever get.